Hello students, I am talking about the fourth chapter of NCERT, moving charges, and I have discussed in previous video Biot-Savart law and Oersted experiment. If you not watched, then click the I button and watch it first. And today's I am talking about the Ampere's circuital law as written on the board. This law is analogous of Gauss's theorem in electrostatics. With the help of Gauss's theorem, we can find the value of electric field in different cases. And here, with the help of Ampere's circuital law, we can find the magnetic field due to open surface. Open surface means just like a planar thing, and closed surface this thing means cube, cuboid, a sphere, and these all that. But Ampere's circuital law is especially for the open surface having the boundary. Open surface, and first of all the assumptions according to the Ampere's assumptions is open surface with boundary. Open surface with boundary. This is the condition or assumptions. According to this law, the line integral of magnetic field, magnetic field around a closed surface, around a closed path, not surface, closed path, around a closed path or closed circuit is mu naught times the total current I threading the closed path, or total current, or maybe you written as total current passes through the surface. You may write here mu naught is the permeability, and this law mathematically represent like this: B dot dl is equal to mu naught times I, and this symbol, the symbol of circle, indicates the closed path. This symbol indicates the closed path. It is nothing, just indication of closed path. Okay, and as you know about the E vector dot ds vector is equal to 1 by epsilon naught times q enclosed, and this is the surface integration, and this is the line integration. And here is the surface. S for the closed surface. This is the closed surface integration, and here is the line integration, closed line integration. This is closed line integration. Here is the closed surface integration, and this is the law of Gauss's theorem. In electrostatics. It gives the mathematical calculation of electric flux, and this is also known as flux. Flux is equal to electric flux. That means phi electric flux is equal to q enclosed by epsilon naught, and you may write this one as a integration method, closed integration method. This one is there. This is in electrostatics, and if you apply the Gauss's theorem in magnetism, then the result is very surprising. B ds equal to 0. This is the Gauss's law in magnetism. Gauss's law in magnetism. To prove Ampere's circuital law, and for this I consider a long current carrying conductor. This is the long current carrying conductor, and this one is the closed loop. This one is the magnetic field from this point to this point. Suppose this is a x and y is the x y is the straight current carrying conductor, and this is triple C, current carrying conductor, and I is the magnitude of current, and A is the radius of this magnetic field lines. Actually, this circle indicates the magnetic field lines. Okay, and this is the tangential direction indicates the magnetic field, and this is the dl vector, just like B dot dl, and this is the magnetic field lines in this direction. For finding the direction of magnetic field lines, hold the conductor and grasp from the right hand, and thumb indicates the just in the direction of current, thumb put in the direction of current, and four fingers as like this indicates the magnetic field lines, and that's why magnetic field lines in this direction as like this. Okay, then mathematically we can say that mathematically B vector dot dl vector is equal to B dl cos 0 degree and closed integration, and as you know cos 0 is 1 and B is constant all over the circle. In all points there is a B. All points the same magnetic field is taken, and this is the dl. And as you know, the value of B due to the long infinite current carrying conductor is mu naught by 4 pi 2 pi I by 2 I by A. This is then mu naught by 4 pi 2 I by A. Integration of this is L, and integration from 0 to 2 pi A, that's why here is 2 pi A. Now it becomes mu naught by 4 pi 2 I by A into 2 pi A. 2 pi, this one is the cancel out. Then it becomes only integration of B vector dot dl vector is equal to mu naught I, and this is the Ampere's circuital law. This is the proof of Ampere's law. Once again, I consider X Y current carrying conductor, and this is the magnetic field around the current carrying conductor, and this is actual surface. This is the in all surfaces magnetic field is there, but I consider this loop for the integration, and this is the B vector, and there are so many elements on this circle, so many elements, and that's why I integrate B dot dl to 0 to 2 pi A, and we get result B dot dl equal to mu naught I, which is the Ampere's circuital law. And now I again prove the Ampere's circuital law for arbitrary path. For arbitrary path. This is a circular path, but I can also prove this theorem, this law on arbitrary path. And for this purpose, I consider again a straight current carrying conductor, and in this time I consider the path is not circle. This is the circle path, but the path is not circle, means something is twisting here and here, this type of path. I consider this type of path arbitrary path. It is not a circular path, and I want to integrate this path b dot dl, and the from center, suppose this is the r1 and this is the r2, and this angle is d theta 1, and another case is just like this r3 and this is the d theta 2. Okay, and there are so many angles, d theta 1 plus d theta 2 plus d theta 3 and so on. The sum of all angle becomes 360 degree or 2 pi. Why? At circle, if you integrate to all angles, then it becomes 360 degree. Just, and then mathematically we can integrate whole closed loop, and the value is b dot dl. Just I want to find the b dot dl for whole closed loop. Okay, and for this we can integrate. This is the b vector. Suppose this is the b vector, and here is also the dl vector. Somewhere is also here b vector. Another, this one is the b1, this one b1. Here is the b2, and this is the d2. And there are so many segments here in all segments, and we can integrate all segments b dot dl, b dot dl, b dot dl everywhere on this path. And I want to find what happens about the result. Then this is the b1 dot dl1 vector plus b2 vector dot dl2 vector plus b3 dot dl3 vector, and so on. So many elements. And this is the b1. b1 means mu naught by 4 pi. Oh, first of all, I consider a angle b1 dl1 cos 0 degree, because dl and b is always in same direction. That's why I consider here, I taken here 0 degree, and this is the b2 dl2 again cos 0 degree plus b3 dl3 again cos 0 degree, and so on. And this becomes b1 dl1 plus b2 dl2 plus b3 dl3 and so on. Okay, and b1 is here for the straight current carrying conductor. Similarly, mu naught by 4 pi 2i. I is same, but r1 is changed. That's why r1. b2 is equal to mu naught by 4 pi 2i by r2. b3 is equal to mu naught by 4 pi 2i by r3. Means b1, b2, b3 is variable at every point, and that's why here is mu naught by 4 pi, okay, 2i dl1 by r1. Arranging this term only, mu naught by 4 pi 2i dl2 by r2 plus mu naught by 4 pi 2i dl3 by r3 and so on. Mu naught by 4 pi 2i taken out, and dl1 by r1 plus dl2 by r2 plus dl3 by r3 and so on. And as you know, the value of mu naught by the value of these all things you may write d theta 1 plus d theta 2 plus d theta 3 and so on. Why? The question is, then suppose that, as you know, angle equal to arc by radius. Angle equal to arc by radius, as you know. Here angle is d theta and the arc is dl and radius is r1, dl1 then r1, then d theta 1 is dl1 by r1, then in the place of dl1 by r1 it becomes d theta 1, dl1 by r1 becomes d theta 1, then dl2 by r2 d theta 2, dl3 by r3 is d theta 3, and so many segments you consider here, so many segments, and all angles, the sum of all angles become 60 degree. Okay, it becomes 60 degree, means 2 pi. From equation this, the mu naught by 4 pi 2i and into what? 2 pi. Then 2 pi, 2 and 4 pi is cancel out. Then it only remains mu naught I. Then the equation becomes v vector integration of v vector dot dl vector is equal to mu naught I, mu naught times I. This is the Ampere's circuital law, required equation. This is the Ampere's circuital law. This is the required equation. Then this law is applicable, means Ampere's circuital law is applicable for any types of closed path. Either it is circle or either it is any arbitrary path. Just it requires the closed path. Okay, means line integration, boundary. So open surface having the boundary, open surface having the boundary. The first assumptions of Ampere's circuital law, the magnetic field lines must be a boundary. Okay, means closed loop. This is the closed loop, and Gauss's theorem is the closed surface, but here is the open surface, not closed surface. It is the open surface having the boundary. You once integrate from one point to the other point in a closed loop, then you always find equation v vector dot dl vector equal to mu naught times of I. Now our next topic is application of Ampere's circuital law. Applications of Ampere's circuital law. The first application, to find magnetic field at a point due to a straight current carrying conductor. This is the topic, and this derivation I have done in first video by the integration method. You may see in first video of magnetic effect of current, and here the same thing derived with the help of Ampere's circuital law. It becomes so easy. How? Just you see, I consider a current carrying conductor I, and we want to find a magnetic field at this point, and for finding this you draw a circle, means closed path. You find a closed path, and we want to find here magnetic field. Then you draw a circle with the radius something a, suppose that a, and as you know, the tangent on magnetic field lines gives the direction of magnetic field, and this is the dl vector for a small element. And now, as you know from Ampere's circuital law, the closed integration of b dot dl is equal to mu naught I, as you know. And from mathematics, we can find the value of b dot dl. Then v dot dl is v dl cos 0 degree, as you know, because b and dl is in same direction, and b is constant, then take off from the take out from the integration, and this is the dl, and this integration must be from 0 to 2 pi a, because 0 to circumference means 2 pi a. Then this is the b and this is the 2 pi a. Okay, and this value equate with the equation 1, means Ampere's circuital law. So from equation 1 and 2, from equation 1 and 2, we get b into 2 pi a is equal to mu naught I, and this becomes mu naught I becomes b is equal to mu naught I by 2 pi a. But this is not a format of our requirement, and that's why you multiply 2 and divide by the 2. Then mu naught 2i by a, and this is the 4 pi. As you know, this is our required equation. This is the magnetic field due to long straight current carrying conductor, and it is very simple. And as you saw in first video, the value to find the magnetic field due to a straight current conductor is too lengthy. Okay, and with the help of Ampere's law, we can easily derive the value of magnetic field due to a straight current carrying conductor. Once again, you write the Ampere's circuital law, this equation, and again you calculate the b dot dl along whole closed path, and this equation equate and find the result of magnetic field due to current carrying conductor. And this is the magnetic field, this is the magnetic field due to a straight current carrying conductor. And you know the formula mu naught by 4 pi I by a sin phi 1 plus sin phi 2 by the integration method. Here consider a long means infinite long. Infinite long means alpha phi 1 equal to phi 2 equal to 90 degree, and that's why b is equal to mu naught by 4 pi 2i by a. This is the straight current carrying conductor. The second application is magnetic field due to solenoid. Magnetic field due to solenoid. Then first of all, I defined solenoid. What is solenoid? Solenoid is a helical structure. Solenoid is a helical structure of insulated wire wound around a cylindrical non-metallic object. Okay, non-metallic object, and this is called solenoid. But whose diameter, one thing is more here, whose diameter is less than its length. Actually less than means much less than, बहुत छोटा होना चाहिए, लेंथ ज्यादा होना चाहिए और डायमीटर इसका बहुत कम होना चाहिए. तो वैसे हेलिकल स्ट्रक्चर को हम सोलेनॉइड कहते हैं. 10 क्लास में बड़ा कन्फ्यूजन होता है कि किधर नॉर्थ रखे किधर साउथ रखे, है ना. ये डायग्राम बार बार पूछता है एग्जाम में और मैक्सिमम स्टूडेंट गलती करता है. तो इसके लिए क्या करना होगा कि एक पहले सोलेनॉइड लिखिए इस तरह का. ठीक, ये सोलेनॉइड है, इसमें जितना लंबाई ले सकते हो उतना ही अच्छा होगा, है ना. बहुत लंबा होना चाहिए. जो हम अभी पढ़ाने जा रहे हैं उसका कंसिडरेशन यही है कि सोलेनॉइड जो है बहुत लंबा होना चाहिए इसके डायमीटर के अनुसार, मतलब इनफिनाइट लेंथ का भी आप समझ सकते हैं इसको, है ना. तो अभी वैलिड होगा. तो हम एक बैटरी लगा दिए इसमें. सपोज I connect a cell, and this is the key for protection of the cell of the circuit. This is the I, this is the I, and current flows in upper portion in outward direction and in downward portion in just inward direction. Means here is as like this, and here is as like this, and this is, you consider this line, this line, this line, this line. Means just outward, inward, outward, inward. Each in every term, upper portion is outward and lower portion is inward. Current carrying conductor. This indicates the direction of current carrying conductor. Direction of current carrying conductor. Here is also direction of current carrying conductor. Don't confuse direction of magnetic field. Direction of current carrying conductor. It is clear. And in upper portion, the magnetic field is current carrying conductor is outward direction, and lower portion current carrying conductor in downward direction. As like this. This is the upper portion, this is the lower portion, this is the upper portion, this is the lower portion, and I consider only 3 sections here. Only 3 sections. For to explain, here is B equal to 0, here is B equal to 0, inside this B equal to constant, and here is B equal to 1 by 2 of inner side, B dash. Yani B end. Okay, but the proof of these things I will discuss in chapter number 5. Here I use it. Okay, how B equal to 0 here? Just you look. This is the current carrying conductor. This one is there, and the blue circle I denote magnetic field lines. This is the I denote magnetic field lines. This circle. This is the magnetic field line. This is the magnetic field line. This is the magnetic field line. Okay. This is the magnetic field line. These are all the magnetic field lines. Blue colors. In blue colors, magnetic field lines. Magnetic field lines. आपको पता होगा कि अगर कोई भी करंट का, और ये जो रेड कलर दिख रहा है, ये रेड कलर जो आपको दिख रहा है, ये करंट कैरिंग कंडक्टर है. करंट कैरिंग कंडक्टर है. स्ट्रेट मान लीजिए, स्ट्रेट करंट कैरिंग कंडक्टर है ना. तो ये जो ऊपर पोर्शन है, ये आपके तरफ करंट जा रहा है. मतलब अगर हम इसको ऐसे पेन को रखें, तो थंब को रखेंगे डायरेक्शन इन द डायरेक्शन ऑफ करंट, एंड फोर फिंगर गिव्स द डायरेक्शन ऑफ मैग्नेटिक फील्ड लाइंस. हियर इज current carrying conductor, and this is the magnetic field lines, means in this direction, just like in this direction. Means here it is in upward direction, magnetic field in upward direction, here in upward direction, and then here is the lower direction, then here is upward direction, here is lower direction, here is upward direction. In this case, in lower portion case, current is goes into the board, then magnet in lower down direction, as like this. Lower down means in downward direction, the magnetic field in downward direction, as like this. This is in lower direction. In this case, upper direction, lower direction, upper direction, lower direction. Okay, here is the lower direction, then here is the upper. This one, this one, this one. Very good. And as you know, the tangent of this is magnetic field. Here is magnetic field. Here is also magnetic field. This direction, here is magnetic field, here is also magnetic field. Okay, and the same magnitude, because current is same, radius is same, all things same, then magnitude of B is also same. And this B is opposite to this B, and this B and this B is cancelled out to each other, because it has equal magnitude and opposite direction, and according to the vector summation law, it should be cancelled. Okay, then the whole things just create a magnetic field lines in this direction, in this direction, in this direction, and that's why inside the magnetic field lines B becomes constant. Here is 0, but this is the other story. and I will discuss in the next chapter. This is the half, and half becomes due to some other reason. Okay, then I will not discuss here this term, but here is B constant, and here is B constant, here is B0. B0 due to the cancellation of equal and opposite magnetic field, and that's why it is cancelled. And this is why in just like this surface and all this type of current carrying conductor makes a magnetic field lines in this manner, as like this. This is the magnetic field lines, as like this. This is the north, this is the south. Because here is, as you see, magnetic field lines here, and the combined effect of all these loops, the north pole in this direction and south pole in this direction. And simply you want to find the north and south pole, then you hold a current carrying conductor or solenoid in your right hand, okay, just, and put the thumb along the solenoid and curl the forefinger in the direction of current, okay. Suppose the current in this direction as shown in figure, then this is the curl the forefingers in the direction of current, then thumb gives the direction of north pole, and this is opposite is the south pole. Okay, once again, just stretch the right hand palm and hold the solenoid just like, and curl the forefingers in the direction of current, then thumb gives the direction of north pole. Easily you can find. Or if you are still in confusion, then think as like this, in which direction magnetic field lines means, once again, this is the magnetic field lines, okay, and the straight current carrying conductor is here, this, and here is this and this, and magnetic field lines is in upward direction in this case, or in this case lower direction, in this case upper direction. In this case is lower direction, and in this case upper direction, in this case lower direction, in this case upper direction. Then this magnetic field is increased, radius increases, as like this, increases, here is also increases, and finally the direction of magnetic field, as you see here, if the combined effect of these two straight current carrying conductor, it becomes as like this. This becomes north pole and this becomes south pole. Once again, I draw a solenoid, long solenoid, as like this, long solenoid, and we want to find the magnetic field due to this long solenoid. This is the long, you can consider as an infinite long, you can consider, because this is the well valued for the long solenoid. And for this I consider a loop. As you know, Ampere's circuital law is applicable for the loop, and that's why I consider a loop. P, Q, R and S. And according to Ampere's law, the B integration of B vector dot dl vector is equal to mu naught times of phi. This is equation 1 according to Ampere's circuital law. But mathematically we can find the value of this. We can find the value of B vector dot dl vector is equal to, means PQRS, closed loop is PQRS. Then first of all, I want to find B vector, this one is the B, and B vector dot dl vector, and a P2Q, just write here PQ. And the second is B vector dot dl vector along QR. Okay, plus B vector dot dl vector across RS. And here is, I am not writing here loop because it is not a loop, and that's why I am not circulating the symbol. And this is the next is the B vector dot dl vector is from S to P. There are 4 arms and 4 equations just like this. B dot dl is, in this case here, B is in this direction and dl is also in this direction, means theta equal to 0 degree. Here is B in this direction and dl is in this direction, then theta equal to 90 degree. And as I explained earlier, B equal to 0 here, and in this case magnetic field in this direction and dl in this direction, then theta equal to 90 degree. The story is the BDL cos 0 degree. This is the value of this term, and this is the QR. Then, as you know, BDL cos 90 degree, and it becomes 0. And this is the magnetic field is 0. Magnetic field is 0. There is no need to integrate or something other. B dot dl cos 90 degree. Then also it is 0. Finally, this term, this all becomes 0, and only the integration of B dot dl mathematically we find B dot dl PQRS is equal to integration of B dl. This one is, and this is the length of solenoid. L is the length of solenoid. This L is the length of solenoid. Then PQRS is, B is take out because it considered as a constant, and dl is becomes L, then BL. Then integration of B vector dot dl vector equal to BL. Equation number 2. And comparing equation 1 and 2 from equating equation 1 and 2, okay, then mu naught I is equal to BL. But our purpose is not solved here. Why? Mu naught I by L. As you know, I is a threading current. And what is the meaning of threading current? And just I will discuss here. Threading current means, this is the threading current I. Thread means dhaga. Threading current. This is the threading current. Okay, just this one is the I current I. Means the number of turns per unit length is N, and this is the total number of turns into I. Means N is number of turns per unit length. Turns per unit length. NL is total number of turns. Total number of turns of solenoid. Okay, and I is the current, and the threading current becomes NLI. This is actually, if you consider I dash, then you write the I dash, because I dash is threading current. This is the I dash, threading current, and that means I dash is equal to NLI. And you can put here B equal to mu naught by L into NLI. I cancel, L cancel, I naught, L cancel. Okay, then B equal to our required equation is NI, mu naught NI. This is the standard formula of magnetic field bell inside solenoid, and it is constant. Mu naught Ni. At the end, as you use. told earlier, at the end it is 1 by 2 mu naught Ni, and it may be it will be proved in next chapter. Okay, and B equal to mu naught Ni, then at end equal to 1 by 2 mu naught Ni. Okay, this is the magnetic field of solenoid and second application of Ampere's circuital law, or it is called toroidal solenoid. Solenoid. One end of solenoid connected with the other end, known as one end of solenoid. Solenoid connected with other end of solenoid. Other end of solenoid known as toroid. Known as toroid. Known as toroid. And in another way, an insulated wire. An insulated wire is wound over a non-metallic ring known as toroid solenoid. Known as toroid solenoid. As like this. Suppose this is a non-metallic ring and you can just turn around as like this. Okay, this. And if you consider a current just goes in the wire, this is the coil and current is I, then current in this way is just goes down, and here is the again goes up, again here goes down, and here is again goes up, goes down, goes up, in this way. Okay, then just like a ring is formed in this way, a ring is a round ring. The current carrying conductor in upper way is this like, lower way is this like, upper way is this like, and the magnetic field of one and to the other conductor cancel out each other, just like it inside, and this is the current carrying conductor, current is inside, then this is the direction of magnetic field lines in this way, and both are cancelled to each other, this and this cancel to each other, then B equal to 0 here, B equal to 0 here. Only B lies inside the coil in this way, inside the coil, as like in which direction, just you find it in which direction. In our figure, in my figure, this is the current goes inside, in this, at this place, current goes inside, and just come out from this circuit, from this point, goes inside, come out from this, goes inside, come out from this, and this is the current carrying conductor, and this is the magnetic field lines. This one is the magnetic field lines, as like this, magnetic field lines. This is current carrying conductor. Thumb indicates the current, and curl the forefinger as like this, means in this direction, as in this direction, also in this direction, here is, okay. Then magnetic field lines in this direction is B, everywhere B, in this direction. You must focus on the direction of current and where it goes and comes out. In different books, figure looks like same, but the way of current going inside and outside may be different, and that's why direction of B may reverse. Okay, then you focus on the just how a wire is wound over a ring, and in my case the current is as like this, means goes inside, and in this surface goes outside, and that's why current element, just like a current element in this direction, and magnetic field lines in this way. Magnetic field, every current carrying loop or conductor in this way, then final direction of magnetic field in as like this, inside the coil, means only magnetic field exists, only magnetic field exists inside the coil. Outside it is zero. Here is also zero. Here is also zero. Don't worry about this. And you consider a radius is R. Okay. And similarly, threading current. Then what is the value of threading current? Then threading. This is the threading current. This is the value of threading current. How it is threading current? As you know, number of turns per unit length and total length. And total length you may write 2 pi r because it is a circumference. Okay. Then according to Ampere's circuital law, the B vector dot dl vector is equal to mu naught I dash, because here threading, total current is threading current, this. And mathematically you can find integration of B vector dot dl vector, means everywhere B dot dl is again B dl cos 0 degree, B dl cos 0 degree, closed circulation. Then B is constant, the integration of dl is 2 pi r. Equation number 2. From equation 1 and 2 we can write, we can write B into 2 pi r is equal to mu naught, and I dash becomes n 2 pi r. And I also, threading current means NLI, then here is I also, this one is. Okay, then 2 pi r and 2 pi r cancel out, then B becomes mu naught Ni. This is the magnetic field. In both cases, either toroid or solenoid, the magnetic field has the same value mu naught Ni, where mu naught is permeability of free space, N is the number of turns per unit length, and I is the current flowing in the solenoid. If a core is inserted inside the solenoid, then the value of B becomes mu naught Ni, and mu is permeability of a material. Permeability of inserted material in solenoid and toroid. Solenoid and toroid. And this value may write mu naught mu r, because mu r equal to mu by mu naught, and then we can write mu equal to mu naught mu r Ni. Means the magnetic field due to solenoid is increased by mu r times. Okay. अब किसी भी सोलेनॉइड को आप लीजिए, एक आयरन रड को उसमें इंसर्ट कर लीजिए, तो उसका मैग्नेटिक फील्ड का प्रॉपर्टी, मैग्नेटिक फील्ड का वैल्यू इंक्रीज कर जाता है। कितना से? म्यू आर टाइम से वो क्या करेगा? इंक्रीज करेगा।